Welcome to lecture number 5 of module 3. In previous lectures we modeled governor model, turbine model, generator model, load model, and we saw that if load is changed in any of the system, then frequency is changed, and that is steady state frequency error exists. So we use that is a secondary ALFC control, and then we found that here we reduce the frequency errors of the system. In whole analysis, we visualize that there is only one generator having its drooping characteristic R, and the damping of the system is D, that is a load variation constant with change of the frequency. Let us take if there are various generators. Of course, it is very much real that in power system in one of the area there will be several generators, and they will be having the different regulation characteristic, that is R, and also D of that system will be 1. So if we are having various generators, let's suppose we are having n number of generators in power system in that one area, then change in the frequency error, that is a del f SS, means steady state error, will be here your minus, that is change in the load in that area, divided by D, that is a coefficient which relates your frequency change with respect to the load change, and R1 and R2 are the characteristic of the individual generators. So here now the B of this system, that is a beta which I was using, now it will be this total value. So the load change here, this D will responsible, if I will go for writing this PL, will be nothing but your minus D change in your FSS. Here minus I can say change in your FSS upon R1, minus here your change in FSS upon R2, and so on so far, minus here change in your FSS upon R. So this is your net load release due to the frequency change, because if frequency is reduced, what will happen? This is negative, then some load will be released from the system, and that load change, that is certain change, will be met, and this load will be met by this component, and the remaining part, you can say this generator will share the load according to this regulation constant, here this R2 and this R1. Already in the previous lectures I explained that if we are going for this, and here for example if the characteristic one is having lower slope and another is having this another slope here, and then this is your steady state frequency, that is where the system is operating, and this where the loading. Now if there is a sudden increase in the loading, what will happen? Your frequency will fall and the load sharing will be now this much. So the change in the loading for this and this will be the different, and again it depends upon this R, that is the slope of this curve, that is a arc here 1 upon R. So we can see which is having this slope here is more, and then we are having less generation. Here you can see if R is more, what will happen? This component will be less. Here if R will be less, then this component will be more, and there so on and so forth. So here in the power system there are the various generators of different R1, R2 are there, so we can relate a change in the frequency will be this. Then we realize that we don't want that, because if the frequency changes here, if load is increased suddenly, what is, let's suppose your load is increased here, your frequency is going and settling here to certain value. We don't want this error, and that's why we use some integral controller, and that is we wanted that this change should come here and finally settle to the 0, means change in your frequency must be 0, means we must update our power system to the normal value, and this rated value, that is a frequency, that is a 50 Hertz in our case. Now let us move, even though I also in the previous lectures just I was giving the concept of the control area. Normally the areas are connected to each other, and the major region, and these areas are connected with the transmission line, and that is called as the tie line. So the tie line control is basically used, and it is connected between the two utilities for the several regions, several advantages. The first one is that over that tie line the utilities can buy and sell power from the neighboring region. For example, let's suppose we are having one region here, this area is 1 and this is the tie line here. there is a possibility another region here and it has a tie line connection here. So this region 1 can buy the power from the area, this region or area 3 over these tie lines. So these tie lines are used to buy or sell. It can also sell power to these areas and again through this tie lines controls. So that's why I have written here this to buy or sell power with the neighboring systems. Another advantage to have tie line control is to meet sudden requirement of power. Means if there is a sudden load increase here, let's suppose change in the load here in this area, what will happen? This load will be met by the generators who are acting here in this area as well as the generators here. They will try to supply over this tie line. So to meet the sudden requirement of the power is accomplished with the help of the tie line control, and overall it improves the composite stability of the system. Means all the system is stable, more stable than not having this tie line control. So it also improves the reliability. For example, let's suppose one generator has gone up, means this generator is tripped. So there is a sudden crisis of load generation in this area, and then we can ask if generators here they are in surplus, they can provide power, and then we can meet the reliability of the system. And also it reduces the installed capacity. As we know, this is one of the advantage of interconnection of the system, that with the help of interconnections we can reduce this installed capacity, or we can reduce the reserve margin. To understand this, let's suppose we have here the capacity of total load here, let's suppose 100 megawatt. This area we are having 200 megawatt. Now to meet this demand, you must have here installed capacity more than that, and let's suppose it's 150 megawatt. Similarly, if it is not connected here with this one, we require here at least 250 megawatt here as well, because if there is sudden variation here and there, we must able to provide that load here. So this is your loading, and then we require here the 250 megawatt of generation. So now the reserve capacity or installed capacity of this one system here is 150. Here is a 250 for this, but if you are going for the interconnections, then what we can do, we can have only 100 here and the 250 here. So what we are doing, we are reducing the reserve margin, or we can say we have reduced the installed capacity of the system. That is, earlier it was 150 plus 250, it was 400. Now it is only your 350. So it says that if you are going for the interconnection, this is a tie line is nothing but the interconnection of the two areas, and then we can reduce the installed capacity. But it has some inherent problems. First is the control becomes complex, because earlier we were only controlling the generators here in this area and it was the independent control. But with help of the tie line connections, we have to also see the control actions of this one. So now the composite control action becomes complex, and we have to have very good controllers, and also it is not possible to have the manual, we should have the good automatic control. But the control strategies will be complex, of course. Another major problem in this tie line control or the interconnection is that if disturbance occurs in this area, let's suppose there is some fault, if we are not controlling this fault in a very less time, what will happen? This fault will be reflected in this system as well. If the generators keep on oscillating, there is some disturbance here, this area will be also affected. For example, we can see in our Indian system, in the Northern Regional Electricity Board system, that we have the several states like UP, your Rajasthan, Punjab, Haryana, Himachal Pradesh, Jammu and Srinagar, and Uttaranchal. Of course, Delhi is also in that. So if there is a fault in one of the lines in any of the state, almost whole state, all this region are getting disturbed. And sometimes you will fear and you will listen that this line tripping causes the whole northern area in the blackout. So it is always very much true that the disturbance of one system is reflected in other system. If it is not there, so it will be not reflected, only one area will be affected. So this is one of the, you can say, major disadvantage of tie line control. But Although we are having very fast and very reliable controllers, they can take care. If one line is tripping, then we can save our system and then we can take advantage of other interconnections here. That these are the advantages. Now let us model, because earlier we modeled the single area system. Now we are going to model the two area system. Here I am considering only the two area, and similarly we can have the other areas as well. So here this is area 1 and this is your area 2. These two areas are connected by a tie line here having reactance X12, and the voltage where they are connected here, it is your V1 angle delta 1. This V1 is magnitude of this bus and angle is delta 1 with the reference to some reference bus. Here the voltage of this bus is nothing but is V2 delta 2, and the power which is flowing from area 1 to 2, it is denoted as 1 2, means 1 from 2, from 1 to 2 here. Similarly, if power is flowing here, then I can say it is 2 to 1. So basically this is the P12, it is nothing but minus P21, because only the direction is changed. So let us model this one using this tie line equation. So we can write the power flow equation from area 1 to 2 when there is no disturbance in steady state condition. So I have written the P12 naught, means there is no disturbance. So power will be flowing with this equation. We know it very well. This equation you must be knowing. This P is your V1 V2 upon X sine delta. So this delta is nothing but the angle difference between these two buses, means from higher bus to lower bus. From angle, this we are assuming this power is flowing from bus 1 to 2. So it is your delta here, it is nothing but your delta 1 minus delta 2. So here we have written, and the V1 V2 are the voltages, respective voltage. X is the reactance of that line where these two buses are connected. So this is the V1 V2 upon X12 sine delta 1 naught minus delta 2 naught. Why I am writing naught? Because we are talking about the steady state, there is no disturbance. So this is the initial angles of these buses. Now let us see, there is some disturbance in any of the area, and the power which is earlier flowing here, this P12 naught, now it is changed, it was P12 naught, now it has changed, it is your P12 naught plus some change in P12 due to the disturbance in any of the areas, either 1 or 2. So I can write now the net power flow from area 1 to 2, it is your the steady state value plus some change. Again it depends, this value is positive or negative, it all depends, that's where is the disturbance, where the demand is more, so power can go this side or that side. So this value may be negative or positive accordingly. So we can write here what we are assuming. The assumption is that voltage magnitude of the systems are constant. So we are assuming the V1 V2 are constant, although this assumption is not very much valid, but normally the power flow, if the real power is changing, so the voltage are constant and angles are changing very much. So we have taken this V1 V2 are constant. Of course the line reactance will be constant, it will be not changed. We are assuming again the frequency, this X is very changed. Of course if the system frequency will be changed, this X will be also changed, but here that variation we can take the same value. Now sine this angle here at was that's delta 1 naught, now it is changed to, basically I can say delta 1 naught will be changed to your delta 1 naught plus some delta angle here 1, and similarly your delta 2 naught will be changed to delta 2 naught plus change in delta 2. So just I have replaced these two angle from here and with the same equation. Now we can simplify this, means I want to write what we can write here. This component we can write this sine, now here delta 1 naught minus delta 2 naught in one bracket plus change in the delta 1 minus change in delta 2 in one bracket, and here it is this one. So now we can expand this, this is your sine, so I can say sine A plus B. So what we can write, we can expand this, so V1 V2 upon X12 is the common. So if you are taking here the sine A into cos B, so here the sine you can say this is your angle A, this is angle your B. So the sine A I have written here, delta 1 naught minus delta 2, into here there is one other term, the cosine of B. Now what will be the cosine of B? You can see this is a multiplication of this term. It is nothing but the cos beta is change in delta 1 minus delta 2. We know that already change in the delta 1 is very small value, and again we are subtracting the change in the delta 2. So this value is very small, and you know the cosine is angle is very close to 0, we can take as unity. So we have replaced here as unity. So that's why that term is not appearing and that has disappeared. Another term here now we can write, again this V1 V2 upon x2, this component will be there, into the cosine A. Here cosine A I have written delta 1 naught minus delta 2 naught, multiplication of here this is your sine B, and we know that if again this angle is very small, so I can write here sine beta will be equal to beta if its value in the radian. So this sine is disappeared with the unity and we have taken this angle. Now what is this? You can see from here this is nothing but it is your P12 naught. So from this equation and this equation, now we can write the change in the power, that is P12 will be your second term. You can see here this is your P12, here P12 naught is there, P12 naught is cancelled from here to here, and we are getting this is equal to this component only, and that is written here, means the change in power from area 1 to 2 is equal to V1 V2 upon x12 cosine of angle delta 1 naught minus angle 2 delta, multiplication of the change in angle 1, means change in angle of bus 1 in area 1 minus change in angle of bus 2 in area 2. This coefficient, as you know, in steady state delta 1 and delta 2 knots are constant, V1 and V2 are also assumed to be constant, and x1 2 of course constant. So this component is completely constant, and we can say, we can represent this is equal to your T12, and this is known as synchronizing coefficient or tie line stiffness coefficient, that is T12. So this equation can be written here again, that's P12 is equal to T12 change in your angle 1 minus your change in angle 2 here. Now we want that angle relation with change of the frequency, because your final term that is coming, your frequency, that frequency is related to your the droop characteristic of the generators, and also your D is related to the frequency. So we can write here the change in the frequency, it is nothing but your 2 pi delta f, and delta f is nothing but, I can write here this change in this frequency is your d upon dt, change in delta. So this delta we can write here, this is the value, this delta, and we can write here this 2 pi, the integration of delta f into t, and similarly if you can put here 1, then it is f1, here 2 is f2, means the two areas, if during the disturbance they will have the different frequencies f1 and f2, then what will be the power flow? Of course, if they are connected in steady state, the frequency of these two areas will be equal. So without any problem, we can equate the f1, change in f1 will be equal to f2 in steady state only. During the disturbance, the frequency of this system will be the different, because during the transient period for certain duration. So I can write here your this change in delta 1 is nothing but your 2 pi change in delta f1 into dt. Similarly, I can write a change in delta 2 is your 2 pi here change in f2, that is change in frequency of area 2 with the dt. So we can take Laplace transform, or you can here we had put this value here in this equation, from here we can get this one using these two equations. From these two equations here we can get this. Now if we are taking the Laplace transform, here we can get simply, this is integration, so it will be 1 upon s. So we can get the change in here, means we can get, if I'll write this P12 s will be equal to twice pi your T12, that is your tie line stiffness coefficient, divided by S, because the S will be common here, integration in both, and I can write change in your F1S minus change in your F2S. So this is your tie line model, and let us see how these are related and how we can model this again. So this whole concept, this change in F1 minus F2, that is multiplied by this coefficient, if you remember, 2 pi into T12 upon S, that gives change in your tie line power model. Now we know it very well that the power which is coming from area 1 here, let's suppose you have assumed that power is here going, change in 1, 2 is coming out from this. So this power basically in area 2, it is going to be here, that is a injected. So here if it is a negative, here it is a additive. But these two areas may have the different rating, different base values. So we have to write, if complete the boxes or block diagram in the per unit system. Let us see how we can relate it. So we know that this P12, that is in megawatt I am talking here, why I have written that is written actual value. So the P12, that is the power flowing from area 1 to 2, will be every time will be equal to the negative of area, that is power flowing from 2 to 1. So in the notation here I can say this P12 will be equal to minus P21, we know it very well. Here I can also write this P21 will be nothing but your minus P12 in megawatt. Now if you want to write this P21 in per unit, so we have to divide the base of the area 2, and the base of area 2 is here, let's suppose PB2 here. So this divided by this value we can also write in the per unit of that area, that is area number 1. So in area number 1 I can write here this value, we can represent this P12 per unit multiplied by base of that area, then it is actual value, divided by base of area 2. So here now in per unit I can write, now this it is in PU, this whole derivation, PU is removed, means PU value just we are writing, means change in P21 is equal to some constant here A12 multiplied by change in area P12, and this A12 is nothing but minus here, that is a PB1 upon PB2. So here it is nothing but this is a coefficient that is relates the base of A divided by base 2, and again with the negative sign. So here I have written this base power of area 1 and 2. Now let us combine this with our actual modeling that we have already done, and we know that if we are having the single area, now I am going to write here, if you remember, this is your the area 1, that is we had here, we had this your change in PC here plus 2, here we had the negative, and this value we were getting this your 1 upon R1. Now why I am writing R1? Because this R1 is related, and I am talking this R1 is the combined effect of all the generators in that area. Here that is going to be your governor and turbine constant, that's I can write 1 over 1 plus TGS, and here for the turbine 1 plus TTS. Here this is giving your mechanical power. Here the gain is unity, as I said, the kg multiplied by kt normally set to unity, so I have taken 1. This is coming your nothing but your P turbine power, and this turbine power here is again that is here plus minus this PL which is coming here, that is change in the PL1 of this area 1, means we can write this is for area 1 we are writing, again this is your minus term, again this power from area 1 it is going, then it is again here there is some negative here value corresponding to your, it is nothing but your change in P12. Here all the values are in Laplace, so here it is not that the P12 is a S bracket S, I have removed that, but you have to see this, all these are in the Laplace domain. This value is coming to your model of your power system, and I can say here it is a power system 1, it's your Kp1 divided by 1 plus Tp1 into S, means all the here I can write once here Tt1, all the value we can write 1 here, P12 of course, and here we are getting your change in the frequency of 1, and this is here going to be here. Now again we have another area, so similarly we can write here, that is your similar this area 1. Now we can write for area 2, here this value is coming to your PC, change in PC2. Here again I can write 1 because we are writing everything in 1. So this is your positive, this value is coming here, that is your combined effect of this droop characteristic of area 2. Now again we are having here your governors and turbine modeling, and here I can say 1 over the Tg2, yes, it's a governor time constant, and here the transfer function for the turbine I can write the Tt2, yes, that is coming here your change in Pt2, and here I can write this. So this value here in that area, if load is changing, this is a plus, so change in PL2, and we know that some power is coming from area 1 here, that is you can say, I'll come to that point here what we are going to write, and then this power system model of your area 2, that is Kp2 divided by 1 plus Tp2 into S, and here that is coming to your change in frequency R2, and this frequency here we know that of this area is related with this governing constant. Now these two areas are connected with tie line, and the tie line model we saw that F1 here, that is coming to here, this is your plus, this is your negative. Now F1 minus F2, that is multiplied by your here the tie line model, that is coming here your 2 pi T12 divided by S. So that here is coming out to be, it is going to P12 here, sorry, and this here is now P21, which is going to be here, of course this is with the negative sign, and we are using some coefficient A12. If you remember, this A12 is nothing but here we are again this P12 we are assuming it is going out, because P21, if you remember here, P21 is the direction which is coming out from the area 2. So some load change there, some generation means generation is here increased, that is your change in the PG. Here the load is also changed, so this is the generation increase, this is a load change, that is mechanical power, and this is going out, so this is negative, and this P12 is related, this P21 is nothing but A12 change in P12. So here just we have multiplied one coefficient. This value is, if both areas having the same base, what will happen? This A12 will be equal to unity. So this A12 is here your unity, means minus 1. If you remember, it was, the value was here nothing but minus PB1 upon PB2, means the base of area 1 to the base of area 2 with the negative sign. If both bases are rated at the same base value, so here it will be cancelled out and we can get minus 1. So what will happen? This minus minus here, then it is a plus. So we can visualize here the whatever the power which is going from area 1, it is going to area 2, and that is related here. So this is your two area system, and again here we are having the primary LFC. Why primary LFC? We can see again in this here the derivation that this case we have connected no doubt this tie lines here, but still there will be some frequency error if there will be change in any one of the areas of the load. So we'll see right now what will be the static performance of this system. What is the improvement? What is the advantage? We can see just right now, and then what we have to do next to reduce this error in this, that is a frequency error in this loop. Now here again this value, let's suppose we are taking to 0, means here we are not changing this reference setting, means we can say this your change in the PC1 is equal to your change in PC2. These are the reference values. If they are kept 0, and let's suppose we are changing the loads, that we are changing, that is your change in the PL1, it is some value, let's suppose your x1 upon s. Why I am writing this x1 upon s? We are taking some input response. Step response means here in this area here, this is your x1, that is changed suddenly, that is your change in PL1. So the PL1 s Laplace transform, it will be x1 upon s, this x1 is magnitude. Similarly, I can write this PL2 s, it is your x2 upon s, and then we can analyze, we can see, we can say this B1 of this area, here it is B1, it is nothing but your D1 plus 1 over R1. Here this B2 factor will be for this area, it is D2 plus 1 upon R2. Now with these changes, we are taking the change in the both area together. So what will be the change in the tie line power? Means we want to calculate this change in P12 steady state and change in the frequency steady state we want to calculate if the both areas are interconnected with the some tie line. So this is your, we have included the extra tie line model here. And other things here, already we model the first area, then it is second area, similar to that modeling, only if the parameters are different and they are connected by one tie line and the tie line models are inserted. Now you can say we have a complete composite block. Now again, since here we are assuming that there is no secondary controller, there is no secondary area load frequency control or automatic load control, so here we are not having any gains and these are 0. So now we can define the steady state values and we can derive it. Here already I explained this, means let's change in the area power in area 1, that is change in PL1s, it will be x1 upon s. Similarly for area 2, power change is your x2 upon s. We know that the steady state value of f1 and f2 will be the same. I said in the transient case only the f1 and f2 will be the different, and that's why there will be change in the tie line power. If the system is in steady state, the frequency of all the interconnected system, it will be the same. So here your change in the frequency during steady state, that is SS, it is nothing but it is your constant and that is a fix for all the regions, and also the steady state change in the tie line power will be also, it will be constant. To understand this, one approach that we can use, as I said, the final value theorems, means we can get this change in the frequency errors here using the final value theorem, or we can simply apply another approach, and here you can see that approach I have discussed here. X1, what is X1? If X1 is changed in the load in area 1, we know if there will be any change in the load in the area 1, that will be supplied by the governor, by changing the governor action. So this is change in the real power of area 1, and since there is some frequency change, so there will be some net load release in that area 1. So here another component minus, that is your P12 steady state value, means here if from area 1 this value is going out, the value which is changed here in the P generation, and some load is released if there is sudden change in the PL. So this PL will be, you can say, algebraic sum of the power here, these should be plus this is nothing but your Pg1, here it is your, that is the damping coefficient, the change in here I can say net load release, here D into change in Fs, and this is your change in your P12 steady state, and this is your change in L. So these two will be equal to the incoming, means algebraic sum of the power at any node will be 0. So with this equation we can write this. It's clear? So it is x1 is equal to your change in Pg1 plus net load release of area 1 minus change in the that power which is in a steady state flowing over the tie line. That can again simplify it. So x1 here we are taking a change in the P12 steady state this side, so we can write x1 plus change in P12 SS, that will be equal to this value. This value we know that what is the Pg1? Pg1 is nothing but change in steady state frequency error divided by R1, that is a composite R1 characteristic of that area 1, minus this D1 again, the net load release coefficient into this, and this is nothing but your minus B1 into your change in frequency SS. Similarly, we can write for area 2. In area 2, here what is happening? In the area 2, there is a, here I am talking that there is some P21 which is going out, there is some load change here, and there is a generation here Pg2, and here another component, that is D2 into FSS. So here also what we can write, this PL change 2, that is X, plus here P21, and this P21 is nothing but we know that it is equal to A12 into change in P12 steady state. We know it very well. So this summation means X2 plus A12 change in area power 1 to 2 in steady state, that will be equal to nothing but this one, this change in Pg2, this value, and minus this value, because this change in the fall, then this will be added, so it is just reverse action, and we can write here nothing but minus beta 2, and this beta 2 is the bias function of that area multiplied by change in the frequency error. Now these two equations, we have the two unknowns, that is, one is your P12 steady state, and we have that FSS in steady state. We have the two equations, there are the two unknowns, then we can solve these two equations and we can get the unique solution. Because the x1, x2 are the given to you, how much they are going to change, these two are not known, A12 is known to you, change in frequency you don't know, but the parameter R1, R2, D1 and D2 are in other words you can say B1 and B2 are known to you, and then we can solve this equation. If you are solving, simply what you can do, you can multiply A12 and subtract, this will be cancelled out, and you can get in change in the frequency error. So if you will solve here, you will get that the change in this steady state, that is here, that is a change in the power from tie line, that is a 1 to 2 in steady state, that will be equal to here B1 x2 minus B2 x1 divided by B2 minus A12 B1, and your change in the frequency error, that is here change in FSS, that is x2 minus A12 x1 divided by A12 B1 minus beta 2, this one. So we can get this expression and this expression separately. Now let us critically analyze, means we see what we are going to achieve from these two. If here I can have the different conditions, let's suppose there is a change in load in area 1 only. So here I can say x1 is there, means x1, let's suppose any value, means we can say here, I can say this PL1 is your x1 is there, but then change in the area 2 will be 0, means that is equal to your x2, means x2 is 0, means only we are considering the change in the area 1 loading. Now with this case, I can say it is case 1, we can go for again analyzing, and then we can get what will be your P12 SS. So for this case 1, the change in the tie line power flow during the steady state, that is a P12, change in P12 steady state will be equal to here this x2 is 0, so I can write here simply minus beta 2 x1 over this value your beta 2 minus A12 beta 1. Now here let us take the base value of both area 1 and area 2 are same, so I can write here A12 is equal to minus 1. So here with this condition 1, 2 in steady state, it is nothing but minus x1. Now what is beta 2? We can write here it is your D2 plus 1 over R2 divided by this B2 plus, now it is in unity, so beta 1 and beta 2, so I can write here it is a D1 plus 1 over R1 plus your this is beta 2 plus 1 over R2. So you can see the change in the tie line power flow here, this is another factor B1 plus B2 is occurring for all the case, but the change in that is occurring the tie line power flow from area 1 to 2. It is here the change in the loading of that area and the factor, that is a bias factor, that's beta 2 of another area. We can again see what will be your change in the frequency here for this case. Here, as I said, your x2 is 0. Here again you can see what we are getting. Here you will see this is nothing but A12 means I can write minus A12 x1 divided by A12 beta 1 minus beta 2. If you put this A12 is this value, here is 2, so we are going to get it is nothing but your x1 divided by minus beta 1 plus beta 2. So in this case you can say now the values are here coming out to be half. This B1 and B2 are added together, and here x1, this minus will be going up, and we are getting this change in the error. So I can say here the change in the steady state frequency, that is your change in FSS, it is nothing but your minus x1 over, that is a beta 1 plus beta 2, means here it is a D1 plus 1 over your R1 plus your D2 plus 1 over your R2, and here this is this concept. Similarly, if there is a change in only area 2, this will be reversed. So here change in F means I can say case 2 where x1 is 0 and x2 is not 0. So I can say this is equal to minus x2 divided by your D1 plus R1 plus your D2 plus your R1, this is R2, and here your change in P21SS will be, now you can see what we are going to get here. From here, if your x1 is 0, so you are getting beta 1 multiplied by this component will be as it is. So I can say simply, and here it is a, now it is a positive, so we can write this here, this value is your x2 into your R1, D1 over 1 upon R1, and here we are getting D1 plus 1 over R1 plus D2 1 over R2. Now you can see, if from this expression, in the previous case, I can say now summarize the case 1 here. Here we are getting the P12 steady state, that is it was coming your minus x1 here D2 plus 1 upon R2, here your D1 plus 1 over R1 plus your D2 1 over R2. Now whenever there was a change in the power in area 1, this component was becoming negative, means the power which was flowing earlier, that is a P12 naught, now it is going to be reduced. Of course that is true, because here this is area 1, this is area 2. If there is load increase here in this area, the power which was flowing, it will be reduced here. Similarly, if there is a change in area here load, then power here will be increased, and that will be area 1 will be supplying the power. So you can say this P12 steady state is the positive value, x2 is positive. If it is increased, then this is all the coefficients are constant. So this will be increased, and means the tie line power is increased. So whenever there is a disturbance load increase here, the power from area 1 will be supplied here. Similarly, if there will be change here, then power change in here in the tie line, means area 2 is supplying the power. So it is a mutual assistant, means one area is in problem, other area is assisting, and that basically improves the reliability and the stability of the system. And the frequency you can see here. To see it very clearly, let us consider that the both areas are almost equal. Means here I can say that is a B1, let's suppose equal to B2. Then we can see how much change in the frequency that is occurring. Now what is this? Now we can see here that is your change in FSS, it is nothing but minus x2 divided by 2 beta, if it is equal to beta. However, in the previous case, if you remember, the change in the frequency error was nothing but your minus x upon the beta. What does it mean? it says that if the both areas are identical and they are connected with the tie line, then the change in the frequency error is reduced by 50%, 1/2 here. And then that is a better. Means if the here change was, let's suppose 0.5 hertz, here now it is only 0.2 hertz. So it is better also. So we can see here, means if the both areas are equal, then the change in the steady state power here in the tie line, that is x2 minus x1, again this value whether it is a positive or negative depends upon which one is higher than that. If both are occurring together, so here you can say x2 minus x1 by 2, and here x1 plus x2, the frequency here change x1 plus x2 by 2 beta. So if x1 is 0, means there is a x2, as I said, here then steady state power is x2 by 2, means the half of power of the load is supplied by the area 2, area 1 here, means power is flowing from the tie line, means when there is a load, let's suppose 5 megawatt is increase in area 2, 2.5 is meeting from area 1. Condition is that here if they are identical. If they are not identical, then some fraction power will be flowing. And the frequency error here in the x2 upon 2 beta. So earlier if they were not connected, it was the case. So we can say the frequency change is reduced by half, and the power flare is also half if both areas are connected together. But in this case we can see we are observing, we are getting still the frequency error is existing, which we don't want. Means in all, even though both areas are connected, if we are not having secondary controllers, only the primary controllers of area 1 and area 2, we are getting the frequency error, although this magnitude is reduced. Earlier it was higher, now it is reduced, but still we don't want. So we have to provide that secondary LFC control for these two areas, and let us see how they are going to be related. To go for the secondary controllers, let us think how the scenario is changing. Now let's take the load change. Means here if you are assuming this area 1 load is increased, plus means increase, and area in 2 load is no change, that is 0. So if here it is changing, what will happen? Load is increased either in area 1 or area 2, frequency will fall. So this condition shows that here it is increasing in area 2, here increasing in the area 2, then frequency is here it is a falling, means frequency will reduce. Once, as I said, load will increase, frequency will fall. So in these both cases the frequency will fall. Now what will be the P net? If the load here, again in the previous expression I showed you that if there is change in the load in area 1, the tie line power which was flowing from 1 to 2, that was net value, was reducing, so it will reduce or decrease, you can say. However, if the load in the area 2 is increasing, so it was increasing. Now what we have to take the control action. So the resulting control action, if the load in area 1 is increasing, then we have to increase the generation in that area, because this tie line is always, we have to restrict that what is the scheduled power that must flow during the steady state condition. So we must generate the load generation in the area 1 to meet the load increase in that area 1, so that there should not be change in the tie line power flow. So the tie line flow is allowed during the emergency condition, during the stabilizing mode condition, and finally we have to change the generation, so that again we should go that here the change in the P12 should be 0. So our concern here that this P net should be 0, means we have to devise the controller that this should be 0, and also we want that frequency SS should be 0. So we have to take the control action accordingly. So what we have to do, if the change in the PL1 is increasing, we have to increase the generation in area 1. Similarly, if the load is increasing in area 2, then we have to increase the generation in area 2, so that this value will be change in the tie line power flow should be 0. Now let us say that if load is decreasing. So if the load is decreasing in area 1 here, decreasing, negative is decreasing. So what will happen? Frequency will increase, means here increase, and load is decreased here. What will happen? This power from area 1, means here it is your area 1, this is your area 2, here that is your P12 net. So if load is decreased here, more power will be flowing here, and that is here it is increased. Then again, to make this condition, that change in P12 in steady state 0, we have to decrease the generation in area 1. Similarly, if there is a decrease in the load in area 2, of course this frequency will increase, and your P net power which was here flowing, it will reduce, and to meet here this value 0, we have to take care, we have to decrease the generation in area 2. So this is the basically, whenever these 4 conditions are possible, we have to take the control actions accordingly. Means whatever the amount of load is changed in that area, that must be compensated by generator in that area only, so that we can have this one. So the first condition to have the steady state tie line power flow 0, we have to increase the generation in that area. And also, it is not only that, if there is some frequency fall, that we have to try to raise it back, so that we have to operate our system on your rated frequency. So the required change in the generation now, that is called area control error, ACE. In the previous case, if you remember, it was nothing but your change, it was change in the frequency. For a single area here, this ACE was nothing but your change in the frequency error, and we were trying to reduce here, that was a negative component, if you remember. Represent the shift in the area generation required to restore frequency and the net power, tie line power flow. So here now ACE is the 2 component. One is your change in the frequency of that area, here earlier it was there, multiplied by this V1 factor, because the V1 is appearing here in this your tie line power. If you see here your this value here in this one, you can say the B1 terms are appearing in this one. B1 upon, if this, let's suppose in area, any one of area, this is 0, some bias factor is appearing there. So what we can do, we can multiply here the bias, and then P1 we can add together. Because this P is the frequency, this is the real power, we cannot add together. Always we must know it. So what we are doing here, we are multiplying some this D, this factor, so this will be the change in the power here, and then we are using this tie line power, it is going to be added. So here now for the area 2, it is your change in the power, that is changing your tie line power flow from 2 to 1 plus beta 2, that is a bias factor. Here it is nothing but this value is your D2 plus 1 over R2. Already I have defined this several times, multiplied by the change in the frequency of that area. So to include this, what we can do now, we have to see, we have to go for integral controller as again. Now what we have done here, this is beta 1, this frequency here, if you remember this is a frequency. Now this I have written in terms of M1 and D1. No doubt you can represent this in terms of your KP1, and this I can write 1 upon TP1S, and others are as it is. Here I have used another factor. Why I have used this factor? Because I have taken, that is the A12, the difference is here, and here I have written 2 pi because I am writing here the F. So there is no problem. So this area control error here, which is coming to your integrator of this area 1 here, this is I2 of area 2, this is your area control error of 2, that is your that here I can say the P12 which is going from here, and this is going to be added, and that is going to be integrated. Why it is written negative? If you are adding, this is a plus, here this is a negative of the gain, and it will be taken care. To see this, now we have to change the reference power. That is your reference power here, that is coming here. This is your PC or PC reference 1 area, and we can write here this reference and minus Ki1, that is a constant of your area 1 integration constant, and we are using the integration because we want that error residue must be 0. So we have to use the integral controller, and we have used the integration here, and that is, if we are integrating, that we are getting 1 upon s. So this is a coefficient plus change in P1 2s plus beta 1 in the change in Fs1. Similarly, for area 2, we can go for another constant here, Ki2, and we are having this coefficient. This value we use, that is your change in P2 1s. Here I have replaced with the A12. Beta 1 is no doubt is equal to here, the B1 is equal to your beta 1, and that is defined here. Similarly, this is defined here. So now in AC1 during the steady state condition, what we are going to get, because our intention that we have to get this AC1 whenever there is a change in the load in particular area, this will be equal to the load in that area, so that we can increase that one. As I said in the control action, whenever there is a change in the loading in area 1, generation will take that loading in that area 1. So here AC1 in during the steady state condition will be equal to your change in the tie line steady state condition plus your beta 1 into change in your frequency steady state conditions, and we can put the steady state condition which we derived earlier. So we can put here the value, that value I have taken from here, if you remember, this values here, here as well as here, and then we can, if we put this value, we will get here this value, and then we can simplify. What is happening, this P delta P12 steady state will be equal to beta 1 into x2 minus beta 2 into x1 divided by beta 2 minus A12 beta 1. Here you can say both are equal, and then it is divided here. So beta 1 x2 is coming here, you can say beta 1 x2 here, and your this value here beta 1 x1 here, and then we can get here this value. Now why here you can see this value is going to be cancelled, here this is the reverse of this. So we can see, and this value will be simply cancelled out. So we are getting x1. So whenever there is a change, means x1 is positive, area error must be negative, so that we can inject that generation and we can go far. Similarly, the area control error here will be also, if x2 is there, then it will be minus x2, and then we can, in this case we can say now during the steady state condition here, this is going to be meshed together, and finally here we will get the change in the frequency error as well as this error, means change in your FSS will be 0, and your change in P12 SSS here will be 0 for the closed loop system. Here we use for the open loop errors. Other way again we can go for similar fashion, that we can use the final value theorem, but that it becomes very complicated because the 2 area and several states, now 9 states are going to be appearing here, so it is very complicated. But we can here use the open loop steady states values in the control area, and now this value is coming to here this, and that is going to be increased. So your of course change in the frequency error as well as change in the tie line power flow will be 0. So we saw now this static performance, now it is 0, that is required. So the bias factor is adjusted such that change in load of particular area should be met by its own area. So these factors are chosen in such a way that we have to obtain these conditions. So means if there is any change, so that area will take care so that this value will be 0, and at the same time we have to maintain the frequency of the system. Another problem here in whole system, this larger value of Ki, means what will be value of Ki? This Ki constant is very critical. As you are going for adding more and more areas, the choice of Ki is very critical. Means sometimes this Ki value, as we saw in the one area control, it was oscillating, it was giving some damping, it was some underdamped modes where and eigenvalues were appearing. So this may give you unstable condition, and therefore we have to design an optimal control utilizing the Ki's and the BS bias factors, and therefore once the Ki is optimally chosen, then we can go for the combined effect with some economic load dispatch, and that is also called the tertiary control. So this KI inclusion is called your secondary ALFC loop. Primary we saw because there was some error, and then we added some integration controller, and then we got the secondary. But if you are going to include your economic load dispatch, then we'll get here the tertiary load control, and that is called tertiary ALFC loop. So we saw primary, secondary, and now it is a tertiary. So we'll see in the next lecture, we'll see the optimal control, how just we can decide to get, so that we can get the stable operation of the interconnected 2-area, 3-area systems together. So to recap, in this lecture, we model the tie line power flow, and we saw what are the various advantages and the disadvantages of your tie lines approaches. If you remember, just I'll come from beginning, just recap you. So we model and we saw that the change, we model here with this tie line here, and we saw that the change in the values here, that is reduced, and finally we say this frequency error. If the 2 areas are there, then frequency error will be reduced rather than a single area condition for the same load change. But again, the frequency error exists, so we have to design some secondary ALFC loop, and then we use this KI, that is, as I said, we have to use this area controller errors and some integration constants here. Integral controllers are used in both area, so that we can minimize the P net change, that is 0 during the steady state, and the frequency also here, that is FSS, will be 0, so that we can have stable and the normal operation of the system. So now, as I said, the gains of these values are very, very critical, and we have to take care accordingly to stabilize this complete system. Now we have the several states here. Once we are going to change, there is a possibility that since generations are changed, why not we can change in such a fashion that we can achieve the economic load dispatch, that is a optimal power flow solution, along with changing whole system. Along with that, we can have the stable as well as economic load dispatch problem. So that we will see in the next lecture. Thank you.